All right, welcome everybody. So we're going to finish off 1-2 by basically just talking about domain and range. Okay. So in order to find the domain of specifically rational functions, so functions where there's a fraction with a variable in the denominator, we're going to have to be able to factor well. So these first few examples are just us going in and practicing factoring. Okay. So when you're factoring a trinomial like this, so this is a trinomial because it's got three things, tri meaning three. You basically look at the last number and you look for factors of that. So in other words, you're going to look for things that multiply to make the last number and include its sign. So we want to know what multiplies to make -5. And then the middle number, you want to know what adds to make that. So I'm just going to put an A here for add and an M for multiply. Okay. Now my brain can't process both at once. So what I like to do is just put down factors of the last number. So the only ways to get -5 would be -5 times 1 or -1 times 5. Notice I'm not putting something like a -1 times a -5 because a negative times a negative equals a positive. And I have to have a negative on this 5. So the signs are really important here, you guys. Okay, and then I'll look at those and I'll say, okay, which of those adds up to +4? So we know that -5 plus, I shouldn't put an equal sign, it's confusing. We know that -5 plus 1 is -4. And then -1 plus 5 is +4. So it looks like the winner is going to be -1 and +5. Sorry, guys, this is a time sign. Kind of squishing it in here because I ran out of room. Okay, so -1 and +5 are the numbers that are going to multiply to -5, but add to +4. So once you've figured out those numbers, we're just going to put them into the blank. Now, there's something I didn't mention that I need to mention now. This is the way that you do it as long as the leading coefficient is a 1. If there's any other number in front of that x squared, then we have a different process called the AC method, where we use factoring by grouping. Okay, so this is the easiest case, the case when there's a 1 in front of the x squared. Okay. All right, let's try this next one. We're just going to do a bunch till we get good at it. Okay, so we're looking for things that multiply to make the last number. So multiply to make -16, and that add to make -6. So I have to think about what multiplies to make -16. -4 times 4, if you add those up, you get 0. So that's not it. There's -8 times 2 or -2 times 8. And this must be the winner because it adds up to -6. The one below it will add up to +6. So that's not the one that we want. So when we go to put these into the parentheses, keep their signs, right? If that's a -8, then it's x minus 8. If it's a +2, then it's x plus 2. Now, you can always check this. When students factor incorrectly, I'm like, well, did you check it? You have a way to know right away if you're right or wrong. So we're going to go ahead and go in here and check to make sure that we, indeed factored this correctly. So the way that you check is by multiplying. This is called foiling or distributing, okay? So foiling, the reason why they use the word FOIL, just to let you guys know, is it stands for first, outer, inner, and last. So basically, we're going to start by multiplying the first. Then we'll do the outers, these two. Then we'll do the inners. And then we'll do the last. This is where the word FOIL came from. But honestly, it's probably easier to just think of, okay, the x has to multiply by both. And the -1 will have to multiply by both. Okay, so I'm going to erase those arrows because I want to do it with you guys, in real time here. So x is going to multiply by x, so we get x squared. And then x is going to multiply by 5, so we get 5x. -1 will multiply by x, and -1 times 5. And the middle terms will always combine, even if you're looking at, you FOILed out imaginary or complex numbers, the middles will still combine. Now, if it matches the original, then you indeed did it correctly. And this does match, so we checked out. Let's go do the same thing on this other one, because it's very powerful to be able to FOIL these and go, yep, I got it. That's the one that's going to do it. All right, so x minus 8 times x plus 2. So x times x is x squared. X times 2 is 2x. Negative 8 times x is negative 8x. A negative times a positive is a negative. 8 times 2 is 16. So when we combine the inners, we get negative 6. 2 minus 8 is negative 6x. And then we go up here and we check to see if it matches the original. Indeed, it does. So we're sure that we factored this correctly. All right, so we're looking for factors of the last number. So things that multiply to make negative 35. And that add to make 2. Okay, so things that multiply to make negative 35. Negative 5 times 7, negative 7 times 5. And we need it to add up to 2. So this is the one that's going to add up to 2. So that means that we have x minus 5 and x plus 7 as the factorization of this polynomial. All right, so let's go in here and check. So we're going to multiply x minus 5 times x plus 7. All right, let's see if we got it. X times x, x squared. X times 7, 7x. Negative 5 times x is negative 5x. A negative times a positive is a negative. 5 times 7 is 35. So if we combine these together, we indeed do get a plus 2x. So this does match the original. Check. Now this one over here is different. I mean, hopefully you're noticing that the D is different. It's not a trinomial anymore. It doesn't have 3 terms. So we're not going to be factoring this in the same way. I mean, we probably could, but there's just a quicker way to think about it. In cases like this, where you can see that both pieces have something in common, then you're going to factor that thing out. Each term has an x in it. Well, then we're going to take out an x. So if we take out an x from the first term and it was x squared, now it will be x to the first. And if we take out an x from the second term, then just the 4 stays. So this is our factorization of x squared minus 4x. Okay, so let's go in here. We can still check, but completely different as far as how we ended up factoring it. So let's go ahead and take x times x minus 4 and redistribute it. So x times x is x squared. And x times negative 4 is negative 4x. So this does match the original. So we're good to go. So that's called taking out the greatest common factor, which you actually always want to do first. So taking out the GCF. Okay, so this one's a trinomial again. So we're going to go back to this things that multiply to make the last number and add to make the middle number. So multiply to make 72. And add to make negative 18. So things that multiply to make 72. I mean, I know 9 times 8, but that's going to add up to 17, not 18. And so let's say that you're struggling, okay, to find it, which happens, okay. What you can always do is get your calculator out, okay, and you can be like 72 divided by 2, okay, so that'll be 2 times 36, and you'll be like, that's not going to add up to 18, okay. 72 divided by 3, so 72 divided by 3 is 24. 3 times 24 is not going to add up to 18, whether or not I put negatives on them or not, right? And then you might do divided by 4, so 72 divided by 4. 4 and 18. Okay, we're getting closer, but that's not quite it, right? 5's not going to go in, so it turns out 6 is the winner, you guys, by the way. Now, it's not going to be 6 times 12 because that wouldn't add up to negative 18. That would add up to positive 18. It's going to have to be negative 6 times negative 12. because a negative times a negative is a positive. So when you multiply those, you'll get positive 72, but a negative plus a negative stays negative. So that's why we get the negative 18. All right, so sometimes it's hard to find the factors, I'm not gonna lie, but just you have a calculator in my class, and so just be like divided by 2, divided by 3, divided by 4 until you run into the number, and don't stress, you know you're gonna run into it eventually, okay? All right, so then we wanna go in here and we wanna check, okay, does this work? Combine the middles. And then check to see that that matches the original. It does, right? Okay. All right, now this one is not a trinomial, it's a binomial. So we're not going to be factoring it in the same way. And we are going to take out the greatest common factor, okay? But in this case, we have more than just an x. Yes, they have an x in common, right? So we can pull out an x. But these numbers, these coefficients on the terms, they have something in common too. So 2 will divide into both 2, and 2 will divide into 16. So 2 is going to be the greatest common factor, and then an x, so 2x. All right, so if we, now when you're factoring out, you're basically dividing. So sometimes when students are first starting, I'll have them like put a divide underneath, because that sometimes helps students see what's going to be in the blank, okay? So if we do this 2 divided by 2, it's going to be gone. And if you have an x squared on top of an x, right, which is x squared is really x times x, right? Then that's just going to leave you with 1x here, okay? And then 16 divided by 2, that's going to be 8. And these two x's will cancel. So that's one way of looking at it. I'm not sure that's the way that I learned how to do it when I was younger. So I'll show you the way I learned also. But a lot of students really like this method of just dividing by whatever it is you're taking out. So another way that you can do it is just think about, okay, well, if I distributed, what could I multiply by to get me this back? And you can see we already got the 2, but we need an x squared. So that means that we're just going to need one more x here, right? And then there's a plus sign. And so you could say, well, 2 times what will get me 16? So 2 times 8 will get me 16. And then you'll check to see if you need more. If I multiply this, the 2 times the 8 gets me 16. And I have an x also, which is great because I only need x to the first. So we found it. So you can frame it as, what do I need to multiply to get me back to the original? Or you can frame it in terms of division, whatever kind of sits best with you. Okay. And we kind of already did the check, you know, like a lot of times you're just doing this check in your head. But let's go ahead and take 2x and multiply it by x plus 8. So we get 2x squared. We get 16x, and that indeed matches the original. So we're good to go. Okay, I mean, that was by no means sufficient for you to be a pro at factoring by now if it's something that's new to you. So I would definitely look for other resources that are going to help you, you know, get good at that. But it's a good start. Okay. All right. So domain. So we're going to find the domain 2 ways, one given an equation and one given a graph. Okay. And I say as of now in this box, because as you learn more and more functions, you'll have more and more rules. Okay. So this is how to find the domain as of now. So it says if the function is not a fraction with a variable in the denominator, or is not an even indexed radical, then the domain will be all real numbers, or an interval notation, negative infinity to infinity. This is the as of now. We're going to add in logarithms later. We're going to add in other functions that have domain restrictions. And so know that it's actually a little bit more complex than this is right here. But as of right now, with all the functions, you know, this will work. Okay. All right. So if the function is a fraction with a variable in the denominator, then set the denominator equal to 0 and solve to find what x cannot be. Now, why do we do this? Well, we can't divide by 0 in math. Every time there's a 0 in the denominator, right? Like we did this earlier, this is undefined. You cannot divide by 0. So you're setting the bottom equal to 0 to find out what values will make it 0. And you're saying that's what it can't be. That's what it can't be. Okay. Number 2, if the function has an even indexed radical, then set the expression under the radical, known as the radicand, greater than or equal to 0. So let's think about why we do this, okay? If I have a radical, this stuff has to be greater than or equal to 0, because if it's not, now think about what's the opposite of greater than or equal to 0. Well, less than 0, aka negative, would be the opposite of that. And when we try to square root negatives, we get imaginary numbers, okay? Now, if we try to square root 0, that's fine, we get 0. If we try to square root positive numbers, that's fine, we get values out. They may not be pretty values, like 1.4, blah, 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 but we give values out. We don't get imaginaries. So when you set it greater than or equal to 0, you're saying it needs to be 0 and up. I cannot square root negative. So that's why we do it, okay? And that's the difference, is that's what it can be. On number 1, it's what it can't be. On this one, that's what it can be. And you have to make sense of these rules, you guys. Don't just memorize them, because you'll forget them. If you're like, why am I setting the bottom equal to 0? Oh, because the bottom can't be 0. So that's what it can't be. Why am I making this greater than or equal to 0? Because I can only square root 0 and up. Okay, and then these things will stick with you forever. Okay. All right. So let's go ahead and take a look at some examples here. Okay. And I'll write little text boxes and stuff so we can think about what we need to ask ourselves internally, right, when we do these. So what I would ask myself is, I'd say, is it a fraction or an even indexed radical? If the answer is no, which it is, there's no fraction here, there's no radical at all, then the domain's going to be all reals. Now, how we write that in mathematics, when you say everything's okay, we say from negative infinity all the way to infinity. That's how you say all numbers are going to be fine. Okay. All right, let's go over here on this one. We're going to ask that same question again. Is it a radical? Now, is it a fraction or an even indexed radical? Yes, it's a fraction. So we need to set the denominator equal to 0 to see what it can't be. Okay, so we're going to take x squared minus 3x. Guys, we don't care about the top at all. 0 on top is fine. It's 0 on bottom. That's the problem. And now you can see why we practiced all that factoring. This would be, it's not a trinomial. So this is just us factoring out the GCF. So we're going to take an x out because everybody has an x. And then we're going to set each piece equal to 0. So I just moved the 3 over to the other side, you guys, by adding it over, and that's why it became a positive. So these are the things that x cannot be. So if I'm looking at like a number line, right? I always like to use a number line, helps me. 0, it can't be. And 3, it can't be. So this is okay, this is okay, and this is okay. So how we would write that in interval notation is we would have to describe each piece. So just describe this piece. This would be from negative infinity all the way to 0, and make sure you use parentheses because you do not want to include 0. If you put a square bracket on it, you're saying go ahead and include 0. And we just found out it can't be 0. So we're going to put a parentheses on it. Then you use this U for union. Okay, it's like a capital U to talk about now the next piece. So this is going to be the numbers between 0 and 3. Again, all parentheses because we don't want to include 0 and 3. And finally, the last piece is going to be from 3 to positive infinity. And that's going to be the values that you are allowed to substitute in to this equation and get an answer out. Now, again, I feel like pictures really say a lot here. So I'm going to go ahead and put in a GeoGebra. Okay, and we'll look at what this looks like, this exact problem here. Okay, so it was x squared minus 2x plus 1. And this is divided by x squared minus 3x. Now we said you can't use 0. We're like, nope, 0's out. And hopefully you can see, maybe I'll stretch this a little bit. 0 is no good because there's not a value at 0. If you follow 0, x equals 0, there's no value on the graph. There's like a gap right there in the graph, in fact, right? And the same thing's true over here at 3. If you look at 3, there's a big gap in the graph. So we said everything besides 0 and everything besides 3. And that totally looks good if you look at this graph. It's perfect. Okay. All right. So remember, those are the values that x can't. All right, let's look at this next one. And I'm going to be a little repetitive, but I need that repetition, you guys, to get things into my memory. I have a really bad memory. So this is for your learner like me. Okay, so is it a fraction or an even indexed radical? We'll say yes, it's a fraction. All right, so what do we know about fractions? The denominator cannot be 0, right? So set denominator equal to 0 and solve. Okay, so we set the denominator equal to 0. And sometimes you don't even need to do this. Some of you can just visually look at it and be like, well, if I plugged in a 7 there, 7 minus 7 would make the bottom 0. So the answer's got to be 7. Cool. I'm hoping we can get you to that point, okay? If you're not there already. All right, so I'm going to add the 7 over, which will make it a positive. And so we got that x cannot be 7. So let's get our number line out again. We know that x cannot be 7. Then that means we're going to open circle 7, but we're going to allow everything else. So the domain for this function is going to be from negative infinity all the way up to 7 parentheses, because we don't want to include the 7. That's going to give us this piece. And then for this piece, it would be from 7 to positive infinity. These are the values we're allowed to plug in because we'll get actual values out. We don't want to plug in 7 because we would not get an answer if we substituted in 7. So here's what that looks like as a graph. Of course, I'm going to have to pull over. There you go. At 7, we have this big gaping hole. And so we would not get a value out. So let's not plug in 7. Okay. Question of the day, is it a fraction or an even indexed radical, right? Is it a fraction or an even indexed radical? Okay. Well, no, it's not an even indexed radical. It's a cube root. It's an odd indexed radical, right? We said, okay, then at this point in time, it's going to be negative infinity to infinity, right? So no domain restrictions. Means all real numbers. All right, so we're going to go ahead and say from negative infinity to infinity for the domain. We'll talk in a second about the whole even versus odd thing. Just wanted to use it first, and then we'll come in and we'll talk about that. All right, so the question, is it a fraction or an even indexed radical? Yes, it's a fraction. So we need to set the denominator equal to 0. Solve. Okay. All right, so we're going to go ahead and set that denominator equal to 0. And again, we can see why we opened up this section by factoring. So we need numbers that multiply to make negative 3 and add to make 2. Let's see here. That would have to be 3 times -1. 3 times -1 is -3, but 3 plus -1 is 2. So it's going to factor as x plus 3 and x minus 1. And then we set each piece equal to 0. So we're going to set this guy equal to 0 and this one equal to 0. So you end up getting x equals -3. That's cannot be right. And then x equals +1. Those are the values it cannot be. So if we can go ahead and make a little number line and we remove those from the number line. -3 is a no. Should probably move that over a little bit, you guys. -3 is a no. 1's a no. But everything this way is good. Everything this way is good. And everything here. So it looks like our domain, we describe each piece, is going to be -infinity to -3. -3 to, to +1. Union. 1 to infinity. All right. Okay. Is it a fraction or an even indexed radical? Yes, it's an even indexed radical, right? So remember, the stuff underneath the radical has to be greater than or equal to 0. Okay. So x minus 3 has to be greater than or equal to 0. We can't be square rooting negatives. Okay. You cannot be square rooting negatives. Okay, so we're going to take x minus 3 and we're going to set it greater than or equal to 0. We'll add the 3 over to the other side, making it a +3. So what we're saying here is 3 and up is okay. 3 and up is what it can be. Oops. It's a closed circle, you guys, because of the or equal to sign. You're saying, yeah, we can include 3. It can be 3. That's fine. And we're going to go to the right because we're looking at the greater numbers, right? So if we were to describe that, and we'll check when we get done. We can check on this. We would be from 3 all the way to infinity. Now, you're saying those are the values that x can be. So for example, if you plugged a 3 in, yeah, you could do this. This would just be the square root of 0, which is 0. If you plugged a 4 in, 4 minus 3 is 1. Square root of 1 is 1. This is working, right? If you picked value like 2, like why is 2 not okay? Well, if we do the square root of 2 minus 3, we're getting a negative, which means we're getting an imaginary. Okay. Now what this looks like on the graph, square root of x minus 3. This kind of did some weird stuff to the y-axis that I feel like I want to undo right now. So let me go it back up. All right. There we go. So you'll notice the graph is going from 3 and up. Over here where 2 was, we're not getting any value, and that makes sense from the math that we just did. Okay. All right, so you have methods, for solving these. Now let's talk a little bit about the whole even indexed thing. So this slide is I'll title it Why Even Indexed. Okay. So something that we have to make sure that we know is that if we had something like the square root of -4, okay, you're looking for what number times itself gets you -4, and there's no answer to that, right? This would end up being imaginary, right? You'd have to pull the I out, make it a +4, and you could square root +4. What number times itself is +4? 2. Yeah. Now, so negatives under an even root They don't make sense because no number times itself can be negative. You know, like if you took -2 times -2, it's +4. You took +2 times +2, it's +4. There's no way to multiply a number by itself and get -4. Okay. Now, when you start making like a cube root though, well, the negative doesn't become a problem anymore. Okay. If you say what number times itself 3 times gets you -8, there's an actual answer to that, right? It's going to be -2. Sorry. It's going to be -2. I can answer it. Because -2 times -2 times -2. -2 times -2 is +4. But if you multiply that by one more -2, that's going to be your -8. Okay. So the difference between even and odd radicals, you can kind of see here. It's like, well, I can cube root negatives. Oops, I can't square root negatives without getting imaginaries out. So hopefully that helps you understand why we're talking about even indexed radicals only. Okay. So we're going to go ahead and do some examples of finding the domain and range given a graph, okay? So it says right here for the domain, you can find the domain in interval notation by writing the x value farthest to the left first and the x value farthest to the right last. For the range, you can find the range in interval notation by writing the lowest y value first and the highest y value last. And this is only when given a continuous graph, because that's actually all we're looking at in this section. It's a good place to start. Graphs can get more complicated and stuff, but let's say we only have a continuous graph, which means it's all connected, you guys. You don't have like jumps in it or vertical asymptotes or something, okay? All right, and remember that negative infinity and infinity always get a parentheses, okay? All right, so, oh, and right here, for number values, an open circle will get a parentheses and closed circles will get a square bracket. Okay, so let's go ahead and try this, okay? So if we're looking at our domain, we go with green. I always like to kind of highlight. This is -3 here, and this is +1 here. So the graph is sandwiched in between -3 and +1. And maybe I would be, okay, I'm just going to leave it at this. So the domain, furthest to the left, comma, furthest to the right. I'll put an L and an R. Now, we said open circles, which hopefully you can see this is an open circle. Those get parentheses, and closed circles get square brackets. So we're looking from left to right if we're talking about domain, and that's because we're talking about x values. But now I'm going to go ahead and highlight the lowest on the graph and the highest on the graph. So it looks like the lowest that this will ever go is -4, and the highest this will ever go is 0. So for the range, we're looking for low to high. So lowest, comma, highest, lowest, highest. And then the lowest is a closed circle. Also the points here too. So this gets a square bracket. And this is where some people might get it wrong. They might put a parentheses on 0 because they're like, oh, look, 0 is not on the graph because there's an open circle right here, right? Get these back really quickly. But you don't want to be looking there, you guys. You want to be looking right here. 0 technically is on the graph because there's a point right there. So 0 is on the graph, which means we need to include it. So we're going to go ahead and put a square bracket on that one too. So I could see messing up on that one because you're like looking here and being like, oh, there's an open circle. 0 is not on the graph. But we find out that it is on the graph right there. Okay. All right, let's try this again. So domain. Furthest to the left, well, there's no furthest to the left because of this arrow, okay? But I can mark where it's furthest to the right, okay? So because I couldn't find a furthest to the left, it just keeps going to the left forever, which means it goes to -infinity. Now, some students might be like, hey, that's +infinity because it's going up. But remember, for domain, you're not looking up and down. You're looking to the left and to the right. You're considering the x-axis, right? The x-axis, if you go to the left, keeps getting bigger and bigger negative numbers, right? -4, -5. So as this graph heads towards the left, it's kind of nice to have a visual. It's heading towards the left, okay? As it continues to head towards the left, on this x-axis down here, it's hitting more and more or bigger and bigger negative values, okay? So negative infinity, and then furthest to the right is going to be 1. So negative infinity to 1. Now, we always give a parentheses on infinity or negative infinity. As for the 1, since it's a closed circle, we'll put a square bracket. Now, for range, since we're talking y values, we want to think lowest to highest. So if I can mark the lowest, it's right here at 0. And I can't mark a highest. That a little more prominent. I can't mark a highest because of this arrow. So it's going to be the same type of thing. It's like, okay, I have a lowest, 0, but it goes up forever. So it's going to go towards infinity. Now I put a square bracket on 0 because there is an actual point right there. Right here at 0, there's an actual point there. So I do need to include it. Okay. Okay. All right. Domain furthest to the left, comma, furthest to the right. I do have a furthest to the left, kind of, sort of. But because of this arrow, it just keeps heading towards the right. So I don't have a furthest to the right. So I should be putting left, right, low, high, left, right. So furthest to the left is going to be 2. Remember, look at the x-axis, okay? That 2 is going to get a parentheses because it's an open circle. Furthest to the right, well, there is no furthest to the right. And remember, if you're thinking to the right, you're thinking about the x-axis. So we're actually heading off to positive infinity. Don't be looking at the fact that the graph goes down, because I don't care about up and down when I'm talking domain. I care about left and right. Now, when I talk about range, that's when I'm going to care about lowest and highest or up and down, right? So the lowest on the graph, there is no lowest. This is just going to keep going down forever. So it heads towards negative infinity because it's going down. And then the highest on the graph is going to be positive 4. That's the highest it's ever going to go. And because it's an open circle, we'll put a parentheses on it. Now, things that open to the left and to the right that just keep getting wider. So things that widen, like this is just going to keep going to the left. It's just going to keep going to the right. Those are going to be your negative infinity to infinities then. There's no furthest to the left point, and there's no furthest to the right point. Now, the range, though, will be a little bit more interesting. Remember, the range is lowest to highest. There is a lowest. This is going to be our lowest on the graph, and that is at -6. And it's actually on the graph, so I'm going to square bracket it. Now, as for the highest, it just goes up forever, and it heads towards infinity. There is no highest. All right, this parabola on part E, again, it just keeps opening to the left and getting wider and wider. It keeps opening to the right and getting wider and wider. So negative infinity to infinity. That's our left and right. Now, as for the range, this one doesn't have a lowest. It just goes down forever. So negative infinity is what we'll put in that spot. Now, as for the highest, it does have a highest. The highest it ever goes is 8. And we will include the 8 because it's actually on the graph. Okay, our last one. Domain, so furthest to the left, which looks like it's 1, 2, 3, 4, 5, -5. And furthest to the right, looks like it's 1, 2, 3, 4, 5 again. So our domain is going to be from -5 to 5. The -5 is a closed circle, so we're going to square bracket it. The +5 is an open circle, so parentheses. All right, so then for the range, we're thinking lowest to highest, right? Forgot to put left to right, left to right. And now we're going to do lowest to highest. So the lowest that the graph ever goes is this point right there, right? And that's 0. The highest that the graph ever goes is 1, 2, 3, 4, 5, is 6 high. So this is 6. So 0 to 6. 0 is on the graph, but the 6 is not because of the open circle. Okay. All right. So that is the domain and range when you're given a continuous graph, how to think about it. All right, you guys, thanks for joining me, and finished off 1.2. So catch you next time in 1.3.